9.3 Definite integrals, areas under curves. So before we were looking at the indefinite integral, which was where x could be anything. Now we're looking at our definite integral. And here it's the area under a curve here between x is a and x is b. So we're looking at a specific area between these points rather than an indefinite area which could continue on forever. And we write this. So we have our a, our lower limit here at the bottom, and our upper limit here at the top. So we have our integral a and b here, function of x dx here. So this is our area under the curve for y equals f of x between x is a and x is b. So the origin of the formula was using here area in the terms of Riemann sums. So here the region between a and b was divided into rectangles here of equal width delta x. And the area is calculated here, working out our product here, our function of xi times delta x, which could be positive, negative, or 0, and then summing all of those areas there, taking the absolute value of any negative products here. And it also was sort of similar to the Simpson's rule, which you may have looked at before as well. So here we look at the fundamental theorem of calculus. So the fundamental theorem of calculus basically says integration is the reverse of differentiation. So this enables us to evaluate our definite integrals directly. So the value of the definite integral can be calculated exactly if we can find the antiderivative of f of x for a function f which is continuous in our closed interval ab. So we write it here, our integral between a and b of our function f of x here dx. Here becomes our antiderivative of our function at point b minus our antiderivative of our function at a. So f is any particular antiderivative of f, and a and b are our lower limit and upper limit. So our upper limit and our lower limit here. And it's always going to be sort of bigger minus smaller, or however we look at it in those ones here. So here we can also write our notation here. So we have between a and b our function of x dx here, and we write it with our square brackets. So here our antiderivative of x, b and a. So we write it this way, and then from this step it moves on to our antiderivative with our points at b minus our antiderivative of our points at a here. So we're going to start by just finding some indefinite integrals as we were before. So here we're looking at here we want integral of x squared plus 2x plus 5. So here it's going to become x to the power of 2 plus 1 divided by that 3 plus 2x 1 plus 1 here divided by 2 plus 5x plus the constant c. So x cubed on 3, our 2's will cancel, plus x squared plus 5x plus c. So moving on to b, same thing, different numbers. So here I want to integrate with 7x cubed minus 3x squared plus 2x minus 24. So here we have 7x to the power of 3 plus 1 more, divided by that 4 here, minus 3x 2 plus 1 more, divided by that 3, 2x, we've got 1 plus 1 more, divided by that 2, minus 24x plus our constant c. Is 7x to the power of 4 divided by 4, minus our 3's will cancel, so x cubed, our 2's will cancel, plus x squared minus 24x plus our constant c. So now we're looking using our limits. So we have our limits of integration, and it's between our two limits, x is a and x is b here. So we're writing here, these are our two limits. So we have our upper limit and our lower limit here. So we've got our integral between 5 and 2. So we're saying whatever our line does, we're looking between our values of 2 and 5 on our x here. So we have 3x squared minus 2 here. So what we can do, so we're using our terminology from here. We're going to integrate and put it here, our integrand here, or our antiderivative here, into our square brackets with b and a here. So we're going to put here our square brackets. 3x squared, we got 3x, 2 plus 1 more divided by 3 here. Our 3's will cancel. So in our next line, that will become x to the power of 3. Minus 2x here, minus 2x. And we notice we don't have to put our constant in now. And we write our 5 and our 2 in, 5 and 2. And so what we're going to do here after this is substitute here in our brackets. So we're going to have, we put our square brackets in, we've got x is 5, so 5 to the power of 3 minus 2 times 5. So we're putting our 5 in for our x values here. Then we're subtracting our 2 values here. So we're going to have 2 to the power of 3 minus 2 times 2. So when we work this one out, we should end up with 111 units squared. So we need to always remember, we don't know exactly what units we're talking about here. We haven't been given that information, but we're finding an area. And so what we need to do is list that as units squared here as an area. So if we move on to our next example here. So we're finding here our integral, we've got between minus 1 and 3. And we've got here root 1 plus x dx. So we'll simplify that a little bit first. We've got between 3 and minus 1, 1 plus x to the power of a half dx here. So now we're going to go through here. We want to find here, put our square brackets in. We've got 1 plus x to the power of a half plus 1 divided by a half plus 1 multiplied by 1 here. And it's between 3 and minus 1. So here we're going to have 1 plus x to the power of 3 on 2 divided by 3 on 2. So here our 2 will multiply up. Here we've got between 3 and minus 1. That was 3. So here we're going to have 1 plus x to the power of 3 on 2 divided by 3. And this is between 3 and minus 1 here. So here we have 2/3 is a constant here. We can take that out the front. So this becomes 2/3. Here 1 plus x to the power of 3 on 2 between 3 and minus 1. So we need to substitute this in. We'll come over here so we have enough room. 2 on 3, and now so we're going to substitute in our values for our 3's. So here we've got 1 plus 3 to the power of 3 on 2 minus 1 plus minus 1 to the power of 3 on 2. Here, so it's going to be 4, 2/3 out the front, 2/3 times by 4 to the power of 3 on 2 minus, so 1 plus minus 1 is 0, minus 0 here to the power of 3 on 2. We don't have to put that in. So we're going to end up with 2/3 multiplied by 4 to the power of 3 on 2, and we put that into a calculator. We should get 16 on 3. Okay, so if we move on to our third example here. Here we want to evaluate. Here we're looking between 4 and 1. We say dx divided by x to the power of 3 on 2. So we said before, well, when we just wrote dx, that meant 1 times dx. So we're integrating between 1 and 4. We've got 1 on x to the power of 3 on 2 here, dx. So we can simplify that a little bit further, and we're going to say here we're integrating between 1 and 4. We've got x to the power of negative 3 on 2 here. So now we have some nicer numbers to work with. So we put it into our square brackets. we've got x to the power of minus 3 onto plus 1, divided by minus 3 onto plus 1, between 1 and 4. So here this will become x to the power of minus a half, divided by here minus a half here, between 1 and 4. So here x to the power of minus a half, so if we come back over here, so we have lots of room here, so x to the power of minus a half becomes here 1 on root x here. And we're here, our 2 multiplies at the top, so we have 2 and it's a negative. We have minus, we'll just clean this up, so we should end up with minus 2 on root x here, between 1 and 4. So if we put our values in here, so we're saying first we've got minus 2 on root 1, minus 2 on root 4 here. So here we're getting, this will become negative 2 minus negative 1. So it's negative 2 plus 1 will give us negative 1 here. So moving on to example 4. We're doing the same thing, just with different numbers. And here we notice we're actually integrating between 1 and 1. So between 1 and 1, we have x to the power of minus 4 dx. So this becomes x to the power of minus 4 plus 1. So it becomes minus 3 divided by minus 3 here, between 1 and 1. So here we're saying x to the power of minus 3 on minus 3 between 1 and 1. This will become here minus 1 on 3x cubed here, between 1 and 1. So now we can we'll go over here, we're going to put our values in. So we have minus 1 on 3 times 1 cubed, minus 1 on 3 times 1 cubed. So we can see that these will be the same. We end up with here minus a third plus a third. So negative times a negative there is a positive, will be equal to 0. And this brings us into some of our properties of integral functions here. So we look at our properties of integral functions. When we have here, we're integrating our function f of x plus g of x, we can treat these separately here. We can treat them separately or together, as we did before. If we're looking here at an integral where our limits can be interchanged, integrating between a and b, f of x dx, we can put a negative out the front and switch our a and our b around here. When our two limits are the same between a and a, then our area will be 0. So we can think of any sort of curve here. We're looking our area under 2 of the same point here, if they were both 1 or both a, we're not going to have any area under there. When we have an integral of a constant multiple of a function, so here integrating between a and b, k f of x dx, we can take this k out the front here as it is a constant. And here we're going to look at an integral of component parts of the limits a and c. So between a and c for our function f of x is the same as between a and b and then b and c. So we're looking here, any sort of curve, we have a, b and c. Our integral between a and c is the same as a and b plus b and c. Okay, so next we're going to find the area of the region between y is equal to x multiplied by x minus 1 squared here. So what we're going to do first of all is try and find out about our curve here. So here we have y and we multiply it through x minus x cubed. So we look at this, we go, okay, this is what our actual y function here is. If we differentiate this, dy on dx here, that will give us 1 minus 3x squared. And if we set this equal to 0, 1 minus 3x squared is equal to 0, 3x squared is equal to 1, x squared is equal to a third, so x is equal to plus or minus root 1 on 3. And so if we write this out as numbers, it's going to be 0.58 or negative 0.58 here. If we look at our second derivative now, we'll stay in blue here. So here we're going to we'll put it over here. So d squared y dx squared here, our 1 will disappear, won't it? So here 2 times 3 minus 6x here. So when we set minus 6x equal to 0, we end up with x is equal to 0. And so this is our point of inflection. So we have our two stationary points here, and if we substitute this in on our d squared y on dx squared here, so for 0.58 we're going to find that this will be negative. And for negative 0.58 we're going to find it's positive. So here negative, that's going to be a max, and positive, this will be a minimum. So now we've got a fair bit of information about our actual curve here. We also know here our y-intercept, when we set x is equal to 0, y will also be equal to 0. And when we looked at our original equation here, our x-intercept, here we can have x is equal to 0, or here 1 minus x squared equals 0, so x squared is equal to 1, x is equal to plus or minus 1 there. So if we draw this up as a curve, so we'll draw it in green so we can find it here. So we know we cut through our y-axis at y equals 0, and our x-axis at 0 and plus and minus 1. So we'll say here's 1, here's minus 1. So we have a maximum at 0.58. So that's going to be about here, 0.58. We're going to have a maximum. And this one will go here, oh sorry, 0.58 on this side. Here, this our maximum is going to be at, I think about 0.3, so it's going to go over here. That will be our maximum, and we're going to go here. That was our point of inflection to our maximum, and then continue down here. At negative 0.58, we have a minimum. And here that's about minus 0.77, and then we're going to come back up through 1 and keep going. And we want the area of the region between here, so this is our line that we've just drawn. This is y is equal to x, 1 minus x squared, and our x-axis here. So we're going to be looking at this area here and this area here. And we're going to be taking these as two separate sections here, because some of this will be positive area and some will be negative area. So to make sure we're not minusing anything out and losing this area, we're going to look at our negative and our positive parts separately. So I'll just move some of this so we can have a bit more space for working here. Okay, so our area we're going to look at as two different sections. So our areas will be between minus 1, less than x is less than 0, and 0 is less than x is less than 1. So here minus 1 to 0, and here 0 to 1. So we're going to integrate here. First of all, we're looking between 0 and minus 1. We've got here, we can use our second part here, so we're going to use x minus x cubed dx plus our other part here. Between 1 and 0, x minus x cubed dx. So we put this into our square brackets here. So it's going to be x, 1 plus 1 is 2 divided by 2 minus x to the power of 4 divided by 4. Between 0 and minus 1 plus the same x squared on 2 minus, no, here, minus x to the power of 4 on 4 between 1 and 0. So we can now substitute some of our numbers in here. So for our first lot, we're going to have 0 squared divided by 2 minus 0 to the power of 4 divided by 4 minus minus 1 squared divided by 2 minus minus 1 to the power of 4 divided by 4. Here plus our second part, we're going to have 1 squared on 2, 1 squared on 2, minus 1 to the power of 4 on 4. Here, minus 0 squared on 2 minus 0 to the power of 4 on 4 here. So we'll change colour so we can see what we're doing. So our first part, this will all be equal to 0. So it's going to be 0 minus. Here we're ending up with 1 squared on 2 minus 1 to the power of 4 on 2. We're going to end up here with minus a quarter. Plus. And here 1 squared on 2 plus 1 to the power of 4 on 4. We're going to end up here with a quarter minus 0. So we put these together, we're getting here, so negative times a negative becomes positive a quarter, plus a quarter is equal to a half square units here for our total area under that curve. So looking at exercise B, we've got here a curve that crosses the x-axis when y is 0. Here, oh sorry, this is our equation here. So here, exercise C. We want to calculate the area between the curve and the x-axis for our function y equals negative x squared plus 1 between x is equal to 1 and x is equal to 2. So here they've given us the curve. They've shown us where we cut through. We cut through our x-axis at 1, and we want to find this here between 1 and 2. So we're going to put this straight into our actual integral here. So we're looking between 2 and 1 for our x values. Our formula is minus x squared plus 1 dx here. So our square brackets, we're going to have minus x cubed on 3 plus x between 2 and 1. So we're going to end up here for our 2 values, minus 2 cubed divided by 3 plus 2 minus 1 cubed on 3 plus 1. So now here we're going to end up here, our first one becomes minus 2/3. And then here our second one becomes 2 on 3 here. And we end up with minus 1 1/3 here. So here we end up, our area is 1 on 1/3 units squared. We can get rid of our minus because it's irrelevant. It's an area is a minus because it's a negative area under the curve there. Okay, so moving on to our next equation here. We're given the equation y is equal to x cubed minus 5x squared plus 4x. So here is our actual curve here. We could go through our steps again to find our relevant parts of our curve, but at the moment we don't really need to. So we're finding out here, we've got 2 parts to do. We want to look here, well, here between 0 and 1. 0 to 1. So we want here 0 is less than or equal to x is less than or equal to 1. And then we're going to look between 1 and 3. 1 is less than or equal to x is less than or equal to 3. So we're going to look at both these parts separately. So our integral here, 1 and 0. Here, and our equation here, we have x cubed minus 5x squared plus 4x dx here. So we can look at this, we get our square brackets here, x to the power of 4 on 4 minus 5x cubed on 3 plus 4x squared on 2 simplifies to 2x squared. Here between 1 and 0. So here we're going to get, for our 1 values, 1 to the power of 4 on 4 minus 5 times 1 cubed on 3 plus 2 times 1 squared minus 0 to the power of 4 on 4 minus 5 times 0 cubed on 3 plus 2 times 0 squared here. So this will work out to be 7 on 12, and this will all be equal to 0 minus 0. Here is 7 on 12. So now for our second part, so we'll change to black here. So now our second part, we're looking between 1 and 3. So here, 3, 1, we've got x cubed minus 5x squared plus 4x dx here into our square brackets, and we can use our equation from before. Nothing has changed, except here between 3 and 1 we're looking. So we substitute our values in. 3 to the power of 4 on 4 minus 5 times 3 cubed on 3 plus 2 times 3 squared minus, we've got 1 to the power of 4 on 4 minus 5 times 1 cubed on 3 plus 2 times 1 squared. So our 1 values will be the same as this. We don't need to work this second part out here. So our first part is going to be minus 6 3/4. Our second part will be 7 on 12 here. So we're going to end up with minus 7 1/3. So our total will be 7 1/3 plus 7 on 12. So we've got here, it's a negative, we're treating it just as an absolute value, it's just an area. So we make it a positive 7 1/3 plus 7 on 12. So this is going to give us 7 11 on 12, or 7.92 units squared. So now we're going to be looking at applications of area under a curve. So one of the applications that we do have in engineering is work done. So here we calculate the work done in moving an object with a fixed force F through a distance of r. So in physics, our work is equal to our force times our distance r joules. If the work is variable, the work done by a variable force F in moving an object between R1 and R2 in the direction of the line of action of the force is given by, work done is the integral F dr. So the area between the graph of F versus R and the R axis. So for example, if we're presented with the situation where the graph is a straight line, so if we had a straight line, the work done would be there. So here, work done by the force and change of energy is through here. Work done is F multiplied by dr. The area under the graph between R is 0 and R is 6 here. Since it forms a triangle, we can use our area of the triangle is a half times 6 for the base times by 12 for our height. So that will be 36 joules. Or using integrals, if graph is a straight line, here our graph F equals 2r. So we can integrate this between 6 and 0, 2r dr. So that becomes r squared between 6 and 0. So 6 squared minus 0 squared is 36 joules. And similarly with kinetic energy here. So a kinetic energy of an object. So it's an energy of motion. An object with kinetic energy can do work. The amount of kinetic energy an object has equals the amount of work that it can do. The amount of kinetic energy an object has equals the amount of work that was done to it to get that energy. So kinetic energy gained is work done giving kinetic energy to a particular mass. So we can integrate our F with respect to dr. So here F is ma dr, so it's m times our change in V on t dr, our integral of m times dr on dt dv, and mv dv. So if we go through here, we integrate this, so it becomes here v squared, we divide by 2, so half mv squared between v and 0. So it's a half mv squared minus a half 0 squared will give us a half mv squared there.